In this module, we shall learn about hypothesis testing using the F-test and the chi-square test. Let us begin by understanding the meaning of statistical inference. The twin branches of classical statistical inference constitute estimation and hypothesis testing. Estimation involves estimation of the population parameter like mean, variance, proportion, etc. from the sample statistic. For example, a manager may be interested in estimating the demand for his product. The concept of hypothesis testing is used when the decision making, for example, by a manager who would want to know whether he could raise the price of his product or not. Similarly, there could be a quality control manager who would like to know whether the number of defective parts is significantly small or not. A hypothesis is a proposition that we wish to verify to know whether it is true or not, and it pertains to the underlying parameter in the population. Hypothesis testing is the process where the data of different types cannot be analyzed in a uniform way unless we use the appropriate statistical tools and techniques to analyze them. There are different statistical tests for hypothesis testing. The choice of the test depends upon the nature of the problem under study, the power of the test, the sampling method, and so on. There are two types of statistical tests, parametric and non-parametric tests. Parametric tests include tests such as the t-test, the f-test, and so on. Parametric tests rely on the assumption regarding the distribution of the parameters in the underlying population. Importantly, it is assumed that the population is normally distributed and has equal variance, hence such tests are more powerful. Non-parametric tests such as the chi-square test, on the other hand, do not make such assumptions regarding the distribution of the underlying population. They are easy to compute and can be used to test relationships between even categorical variables. The following pages will focus on the chi-square distribution and the F distribution as tests of testing the hypothesis. After studying this module, you shall be able to know the concept of hypothesis testing, chi-square test, and F-test. Define a chi-square distribution, understand goodness of fit, and apply chi-square test. Understand F-test, apply F-test, identify the statistical distribution. First, we shall understand chi-square test. Chi-square is the square of the standard normal variable. Let x be a random variable following a normal distribution with the mean as mu and standard deviation as sigma, then z will be equal to x minus mu divided by sigma, which is a standard normal variate. Therefore, the chi-square variate with n degrees of freedom would be sigma I ranging from 1 to n bracket xi minus mu
divided by sigma I whole squared. The chi-square statistic measures the difference between the expected and observed frequencies in absence of any relationship between the variables. Its value is 0. Moving on to the PDF of chi-square distribution, if the chi-square is a random variable following chi-square distribution with n degrees of freedom, then its probability density function is given by the following. P of x is equal to 1 upon 2r nu by 2 bracket x by 2 to the power of nu by 2 minus 1 e to the power of minus x by 2 for all of x greater than 0, for x greater than equal to 0, and 0 for x greater than equal to 0. The graph of the PDF function of a chi-square distribution is shown in the figure. It depends upon the degrees of freedom n, and the shape of the probability curve is shown in the figure. The figure shows that the distribution becomes more symmetric as the degrees of freedom increase.
We next have the fitting of a distribution. But before discussing the goodness of fit of a test, let us understand the concept of fitting a statistical distribution. Very often we are concerned with the choice of an appropriate statistical distribution which can be used to describe our data. Distribution fitting is a process of selection of a distribution that best fits the data. Generally, our data is affected by random factors and we need a probability distribution to deal with risk and uncertainty involved with such data while making policy decisions and business decisions. Probability distributions are applied in fields such as investment, insurance, risk analysis, market research, business and economic research. Since such decisions are prone to risk and involve high cost, it is imperative to choose the best and the most appropriate probability distribution. Any incorrect model can result in serious consequences in the form of loss in terms of time or money or wrong design or wrong policies and so on. Thus, distribution fitting allows for better decision making through the development of valid models. So the question arises how to choose the most appropriate distribution. The choice will depend upon the presence of symmetry around the mean value. For that we can build a histogram and determine whether it is symmetric, skewed to the right or to the left, and use the distribution with similar shapes. Symmetric distributions include the normal distribution, student's t distribution, and the Cauchy's distribution. Distributions with positive skewness, skewed to the right, include log normal distribution, logistic distribution, Gumbel distribution, and so on. While distributions such as Cauchy or square normal etc. are negatively skewed, that is to the left. Once the selected distribution is fitted, we now need to determine how well it fits the data. We can do this graphically by comparing the empirical and the theoretical graphs. We can also conduct certain goodness of fit tests to ascertain the validity of our selected probability distribution. Graphical methods for this purpose include scatter plot, box and whisker plot, frequency distribution histograms, normal probability plots, graph with error bars, stem and leaf plots. Apart from the graphical methods, we can conduct the Kolmosov and Smirnov and Shapiro and Wilks tests to ascertain whether one distribution is significantly different from the other.
Let us now move on to understand the application of chi-square distribution. First is the goodness of fit. As mentioned before, the goodness of fit test is used to check how well the distribution fits the data. This test, developed by Carl Pearson in 1900, is used to test whether the deviation between observation, that is the observed value, and theory, that is the expected value, is attributed to chance or is due to the inadequacy of the theory to fit the data. In other words, it is used to test if the result of an experiment supports the theory or the hypothesis. The goodness of fit test is based on a chi-square distribution. Chi-square equals 0 when there is no difference between the variables. It is always positive when the square of the deviation between the observed and expected frequency will be small, we can claim that it came from the distribution. The test is always right-tailed. Null hypothesis. There is no difference between the observed and the expected frequency. This is given by chi-squared, which is equal to sigma bracket OI minus EI whole squared by EI. This follows a chi-square distribution with n minus 1 degrees of freedom, where O123ON are observed frequencies and E123EN are expected frequencies. Steps. First, calculate chi-square for the data. Second, under the null hypothesis that the theory fits the data and the test statistic chi-squared follows a chi-square distribution with n minus 1 degrees of freedom. Third, search the critical value of chi-square at the certain level of significance. Fourth, if the computed value of chi-square is less than the critical value, then it is said to be non-significant at the required level of significance, and we accept the null hypothesis. It implies that the discrepancy between the expected and observed frequencies is due to chance. However, if the difference between the two frequencies is large, that is, computed value of chi-square is greater than the tabulated value, we reject the null hypothesis in favor of an alternative hypothesis. It implies that the experiment does not support the theory. The figure shows the acceptance and the rejection region to accept or reject the null hypothesis. Here alpha is the level of significance. Let us understand it with the help of an example. The following figures show the distribution of digits in numbers chosen at random from a directory. The test whether the digits may be taken to occur equally frequently in the directory. Solution: null hypothesis H0 is that numbers are uniformly distributed. The expected frequency is 10,000 by 10, which is 1000. The difference between the actual frequency and expected frequency is calculated in column 4 with O minus E, which is the then squared in the next column and then divided by E in the last column. The summation of the last column turns out to be sigma chi squared, which is equal to 58.542. Here n is equal to 10, hence degrees of freedom are 10 minus 1, which is 9. The critical value of the chi-square at 5% level of significance for 9 degrees of freedom is 16.919. Since 58.542 is greater than 16.919, we can say that the null hypothesis is rejected at the 5% level of significance, and it can be concluded that the numbers are not uniformly distributed. Next we have chi-square test for independence of attributes. The test is used to assess whether there is any association between the row and column variable, that is, it is the test of comparison between the frequencies of one attribute variable and other attribute variable. The chi-square test for independence has a null hypothesis as H0 is equal to P1 is equal to P2 is equal to P3 is equal to Pn, where P is the sample proportion, and the alternative hypothesis H1 is equal to the sample proportions are not equal. Let us now look at the steps. First step, here the null hypothesis is the row and column variables are independent. H1, the variables are dependent. Here, unlike the test of goodness of fit, only the expected frequencies are computed to arrive at the chi-square value. Second step, compute the expected frequencies given by row total into column total divided by table total. Then calculate the chi-square using the formula chi-square is equal to sigma of bracket OI minus EI whole squared upon EI. Third step, check the critical value at the selected significance level. Since independence tests are right-tailed, the level of significance of chi-square for alpha with degrees of freedom r minus 1 into c minus 1, where r is the number of rows and c is the number of columns. And the last step is, if the computed chi-square for alpha is greater than the tabulated chi-square for alpha, then reject the null hypothesis, otherwise accept the null hypothesis that the variables are independent. The next application is to test if the population has variance equal to the specified value. Very often we are interested to know whether the population variance is equal to a specified value. For this purpose, we conduct a chi-square test. Here, chi-square is equal to n minus 1 into small s squared upon sigma squared. Here we compute the test statistic where n minus 1 is the degrees of freedom, n is the sample size, s square is the sample variance, and sigma squared is the population variance. Null hypothesis H0 is that the sigma squared is equal to sigma 0 squared, which is the value of the variance under the null hypothesis. If we computed value is greater than the critical value, then the null hypothesis is rejected at the chosen level of significance. It implies that the population variance differs from the specified value sigma squared. Let us understand it with the help of an example. A random sample of size 20 from a population gives the sample standard deviation as 6. Test the hypothesis and find out whether the population standard deviation is 9. Solution H0 that sigma is equal to 9, H1 that sigma is not equal to 9. N is equal to 20, sigma is equal to 6, chi-square is equal to n s squared by sigma squared, which is equal to 20 into 36 divided by 9 into 9, which is equal to 8.89. The critical value for 19 degrees of freedom at 5% level of significance is 30.114. Since 30.144 is greater than 8.89, we can accept the null hypothesis that the population standard deviation is 9. Further, we shall now understand the F-test. R. A. Fisher developed the F-test, also known as the variance ratio test, and is used for analysis of variance to check whether the two population variances are equal or not. If Z1 and Z2 are independently distributed chi-square variables with V1 and V2 degrees of freedom respectively, then F is equal to Z1 upon V1 whole upon Z2 upon V2. This would follow a F distribution with degrees of freedom V1 and V2. We shall now look at the F-test graphically. The shape of the F distribution depends on the number of degrees of freedom. The distribution takes only positive values and is skewed to the right. As the number of degrees of freedom increases, skewness decreases, that is, V1 and V2 increase. F distribution approaches a normal distribution. The square of the random variable having t distribution with v degrees of freedom has an F distribution with 1 and v degrees of freedom respectively. T squared v is equal to F1v. If v2, the denominator's degrees of freedom, is fairly large, then v1f is approximately a chi-squared with degrees of freedom F1. That is, the numerator degrees of freedom times the F value is approximately the same as the chi-square distribution with degrees of freedom V1. We conduct a F test when we are interested to know whether two normal populations have the same variability. It measures the ratio of two sample variances. Let x1, x2, x3 up to xn1 be a random sample of size n1 from the first population with a variance of sigma 1 squared, and let y1, y2, y3 and yn2 be a random sample of size n2 from another population with variance of sigma squared 2. Here the ratio S1 squared by S2 squared follows an F distribution. The null hypothesis is set as H0 is equal to sigma 1 squared is equal to sigma 2 squared is equal to sigma squared, that is, the population does not differ significantly. Alternative hypothesis H1 is sigma 1 squared is not equal to sigma squared. F test is generalized in the case of an ANOVA where F test is used to test whether null hypothesis sigma 1 squared is equal to sigma 2 squared is equal to sigma 3 squared is equal to sigma n squared. The test is equivalent of testing for multiple means. Under the null hypothesis, the test statistic is F is equal to S1 squared by S2 squared, which is approximately equal to a F statistic with degrees of freedom n-1 and n-2. S1 squared is equal to sigma bracket x minus expectation of x whole squared upon n-1. S2 squared is equal to sigma y minus expectation of y whole squared by n2 minus 1. S1 squared and S2 squared are unbiased estimators of the population variance sigma squared. The null hypothesis will be rejected if the computed value is greater than the critical value of F. It implies that the population value differs significantly. Let us understand it with the help of an example. Suppose a company manufacturing tube lights using two different processes M and N is examined. The life of tube lights of process M has a normal distribution with a mean mu1 and a standard deviation sigma 1. Similarly, the process N has a mean mu2 and a standard deviation sigma 2. The data related to the two processes is given in the table where the number, mean and standard deviation of both processes is given. Check whether the two processes have similar variability at the 5% level of significance. Solution. Here the null hypothesis is that sigma 1 squared is equal to sigma 2 squared. The alternative hypothesis is that sigma 1 squared is not equal to sigma 2 squared. The F statistic is given as S1 squared by S2 squared, which is equal to N1 S1 squared upon N1 minus 1 whole upon N2 S2 squared upon N2 minus 1. Now we substitute the relevant numbers. Curly bracket 16 bracket 60 squared whole upon 16 minus 1 curly bracket closed upon curly bracket open 21 into 50 squared by 21 minus 1 curly bracket closed. This is equal to 57600 upon 15 divided by 52500 divided by 20, which is the same thing as 3840 divided by 2625, which is equal to 1.46. The critical value of f at 15 and 20 degrees of freedom at 5% level of significance is 2.20. Since 2.20 is greater than 1.46, we accept the null hypothesis that there is no significant difference in the variability of the two samples.
Let us now summarize what we have learnt in this module. There are two branches of statistical inference: estimation and testing of hypothesis. Estimation involves estimation of the population parameters like mean, variance, proportion, etc. from the sample statistic. A hypothesis is a proposition that we would like to verify as to whether it is true or not in the context of the underlying population parameter. There are two types of statistical tests: parametric and non-parametric. Parametric tests are t-test, f-test and so on. Non-parametric tests are tests like chi-square test. The chi-square statistic measures the difference between the expected and the observed frequencies. Distribution fitting is a process of selection of a distribution that best fits the data. We can check the fitness of a distribution either graphically or through that is tests of goodness of fit. Goodness of fit test is a chi-square test, and it is used in an experiment to support the theory of the hypothesis as to whether it is the proper distribution, does it have a good fitness, goodness of fit. The chi-square test tests for both independence of attributes and compares the frequencies of the attributes of one variable with another variable. The chi-square test is also used to check the population whether it has equivalence of variation to a specified value. The f-test is also known as a variance ratio test, and it is used for analysis of the variance to check whether the two populations have the same variance or not. If Z1 and Z2 are independently distributed chi-square variables with V1 and V2 degrees of freedom, then f is equal to Z1 upon V1 whole upon Z2 upon V2, and it follows a f distribution with V1 and V2 degrees of freedom.